Querying production databases in plain English is no longer a luxury. It is necessary, but how do you build an AI assistant that can queries, generate safe SQL, handle customer support notes, and read real-time streaming data? Today, I am going to show you how I built this multi-agent RAG operational portal running natively on Azure Databricks. We are going to connect a premium glassmorphic dashboard to a Spark structured streaming pipeline, ingest thousands of transaction records on the fly and write them directly into Delta table in Unity Catalog. Then we will configure a team of intelligent routing agents that translate conventional queries into precise read-only SQL before deploying the entire system to cloud using the new Databricks App Container Service. If you want to see how to bridge enterprise data lakehouses with conversational AI, this video is for you. Hello everyone, welcome back to the channel. If you are new here, my name is Shashanka, and on this channel we will build production grade AI and data engineering project using real world technologies. So let's dive in and build this multi-agent RAG operation portal step by step. To understand how this all hangs together, let's look at the system architecture. It essentially splits into two entry parts that merge inside Databricks and then connects to our AI query layer. Let's break it down. The first will be code deployment. On the left side, we have our code base. We clone this repository directly into our Databricks workspace using Git folders. This gives us our Jupyter notebook and Python modules natively on the cluster ready to run. The next will be streaming data ingestion. In the middle, we have our raw data. When raw CSV files like order CSV lands into our landing zone, which is the Databricks file system DBFS raw directory, we have a Spark structure streaming job waiting. This stream autoloader instantly picks up the new CSV file, applies our predefined schema, and stream appends the record into our secure Delta Lake table, which is ABD code data dev AUE. And then it will be agentic RAG querying. Finally, on the right, we have multi-agent RAG layer. When you ask a chatbot a question, the agent don't guess the answer. They translate our natural language query into secure read-only SQL command, query the Delta table natively on the cluster, and synthesize a formatted timeline response. This gives you real-time database accurate answer with zero setup overhead. Now that we understand the architecture, let's jump into the GitHub and take a look at the code base. We have a clean modular structure that splits the local web application from the native Databricks notebook. First up in db.py, this is our data builder. It generates our 500 mock transaction with realistic customer detail, categories, shipping tracking codes, and support nodes. It exports them into order.csv, which we can upload our cloud bucket and sync them to a SQLite mirror, which is orders.db for our local testing. Next, we have agent.py, which is the core intelligence of the project. It defines our router, database lookup tools, and analytics tool. If you provide a Gemini API key in the UI, it orchestrates a live agent tool, which actually tool calling. If you don't, it falls back a smart local NLP rule engine that phrases our query and queries the database using Python regex. To glue this together, locally we use main.py. Our fast API backend server, it serves our analytics, list order, and exposes API chat route that streams agent execution logs and response using server sent events in real time. Under the static folder, we have the web UI index.html for our split screen layout and style of CSS, which implements the glassmorphic dark theme, and app.js, which handles the streaming connection and draws our chat. Finally, we have Databricks DDL.SQL to create the Delta table schema in Azure, and Databricks Notebook IPYB, which is native notebook. You upload directly your Databricks cluster to run the PySpark structure, stream and execute RAG queries. Let's open Databricks Notebook and see how the streaming pipeline works. For this build, you will need an active Azure Databricks Premium Workspace and an ADSL Gen 2 storage container. I won't bore you with clicking through the Azure portal in this video. So, if you need help setting up those, check out the prerequisite guide in my GitHub repo down below. Otherwise, let's dive straight into the code. As you can see, our workspace directory is now a native Databricks Git folder linked directly to our repository on the main branch. The best part is whenever we make changes on update code on GitHub, we don't have to delete folder or re-upload files. You just click this gray branch tag right next to the folder name, hit pull, and Databricks syncs the entire codebase instantly. Now let's open our notebook and start the streaming pipeline. Before we can run any code inside Databricks, we need to spin up a compute cluster. Under the policy dropdown, I select personal compute or unrestricted. If you have the personal compute option, select it, as it locks our setting to single developer parameters and saves you money. For the compute cores, we change this to single node. We do not need a multi-node cluster with workers because of our size is lightweight, and a single node can easily run Spark structured streaming and our AI agents. For the Databricks runtime, select 14.3 LTS or higher. We use a standard runtime, not the ML runtime, which boosts up faster. For the node type, select standard DS3_V2. This gives us 4 core and 14 GB of RAM, which is the most cost efficient instance type in Azure. Finally, this is the most important setting, enable auto termination and set it to 15 minutes. This ensures that if you step away or forgot to stop your cluster, Azure will automatically turn it off, protecting you from unexpected bills. Let's take a look at our local data generator script db.py. The purpose of the script is to bootstrap our environment with mock transactional, so we have a realistic dataset to test with. We import Python standard SQLite 3 library for local database operation and the Faker package to synthesize realistic customer profile. At the top, we define a static catalog of products under 5 main categories: electronics, apparels, home and kitchen, books and fitness. Each item has a predefined unit price. We then define a function called generate data. This runs a loop 500 times, create order ready starting at ORD 1001. For each order, Faker generates a random customer name, email address, phone number and street address. The script dynamically assigns order dates spread randomly across last 45 days and randomly chooses status like pending, processing, shipped or delivered. If an order status is marked as shipped or delivered, the script automatically attaches a shipping carriers like FedEx or UPS, generates a tracking number and compiles a support history log showing the timeline of the order creation, payment verification and dispatch logs. Finally, the script writes the 500 records into CSV spreadsheet called order.csv and mirrors the directly into local SQLite database called order.db. Now let's explain the Databricks schema layout, whether you are running this locally in SQLite or Azure Databricks Delta Lake. These tables are shared exact same column structure. Let's look at the create table DDL script. Like first we have ID, Brighton int, generate always identity, order ID, customer name, email, phone, order date, timestamp, country, shipping address, city, zip code, date, items and support node. If we open the Databricks Catalog Explorer right now, you can see that our order table is successfully registered in the schema, but there is absolutely no data in it yet. Why it is empty? Because our workspace notebook is designed as an end-to-end data pipeline. The table structure is created first, but the actual data won't exist until we execute the pipeline stages. The pipeline has 3 main stages. The seeder stage, overwriting the table with our initial 500 mock transaction records. The streaming listener stage, activating our Spark structured streaming query to monitor our landing zone. The batch generation stage, dropping our raw CSV transaction file into the landing zone to trigger the stream. Let's go back our notebook, run all stages of pipeline and watch the data flow into our catalog in real time. Alright, let's start with step 1 of our pipeline, database seeding and data generation. The goal of this step is to generate 500 highly realistic mock transaction and write them to Delta table in our Databricks Unity catalog. Let's break it down in the code into 3 parts of the libraries. generator loop and the delta lake write. In step 1, we generate our database seeds. In part A, we import Faker and define a retail product catalog. In part B, we run a generator loop to build 500 mock transaction, complete with customer details, order statuses, and transaction timeline. In part C, we convert the data into PySpark data frame and write it directly to Unity catalog as a optimized delta table. This set up our clean database baseline of 500 records. Now let's explain step 2, setting up our ingestion stream. The goal of this step is to set up real-time listener that automatically read CSV file that appends them to delta table. First we clear any old folder data, so start fresh. Then we set up our Spark reader to monitor our landing zone. Make sure the recursive file loop option. Without this, Spark will ignore file inside subfolder. Finally, we start writing the stream table using append mode, and we set a checkpoint folder. This checkpoint is safely net. If our system crashes, Spark uses it to restart exactly where it stopped without duplicating any data. Now our stream query is running in the background, waiting for new file to arrive. In step 3, we define a helper function called generate _ and _ drop _ streaming CSV. This function acts as a simulator. It represents our external e-commerce provider sending new order batches to our system. Inside the function, we generate a fresh batch of transaction and load them into a data frame. The key command is /, and we use / to force Spark to merge the partition files and write to batch as a single clean CSV file inside our landing zone. This gives us a simple way of drop file on demand and test our streamlined pipeline. Now in step 4, we run the stream. We trigger the generator to drop batch A with 5000 orders and sleep for 12 seconds to let the background stream process it. Then we drop batch B with another 5000 order. As you can see from our notebook output, our active database count dynamically climbs from 500 to 5500 and finally to 10500 total orders in Unity catalog. In step 5, we define our database executor execute _ spark _ SQL. This helper is our security gate. Before executing any query received from our AI, it phrases the query string to verify that it is read-only. Selects query. If it detects any modify commands like drop or delete, it blocks it immediately. Step 6. Register the Python tool function that our AI agents can interact with. We define get order details to pull specific column, search order to search names and emails, and get analytics summary. To compute group statistics on the fly, our AI models will use these tools to fetch data instead of trying to make things up. Step 7. Build the brain of our system. First, we write a local fallback function that uses simple keyword patterns to route queries in our API key in rate limit. Below it defines run agent Gemini. Notice that we import the Google Gen AI SDK modules inside the function. This is the crucial safety pattern so the notebook doesn't crash on cluster nodes that do not have the library installed. We pass the tools under the tool configure option, allowing Gemini to run a tool calling loop to retrieve data. Finally, step 8 is our testing playground. We enter our API and write our test queries. When we ask find order for customers Brandon or how many orders are delivered, the agent runs tools called loop queries our 10,500 delta table row in real time and prints formatted markdown summary response. Our pipeline is complete, secure, and fully operational. Now that our pipeline has successfully seeded our Delta table, it is time to deploy our web application live in the cloud using Databricks app. First, go to the left side in Databricks and click on the apps. In the top right corner, click on the blue Create App button. We will select the custom app because we have our own files and startup configuration. Give your app a name, for example, multi-agent track. Next, for the source code location, instead of uploading local files, we point directly to our Git folder that we cloned from GitHub earlier. This links our app directly to our GitHub repository. Anytime we push a new change to main branch, we can sync and redeploy our app with a single click. Now, before we hit deploy, we need to supply our credentials so the app can communicate with Gemini API. Understand the app setting environment variables section. We add a new key named Gemini API key. Paste your Google AI Studio API key in the value box. By doing this, our fast API backend will automatically detect the key on the startup, allowing the chatbot to work right out of the box without needing any manual setup from the user in the UI. Once that is saved, click deploy. Databricks will now read our requirement text, install all the Python packages, read our startup command in app.yaml and boost up our fast API server. Once the status indicator turns green and says running, click the app URL and your live cloud-hosted multi-agent operation portal is ready to go. To power the intelligence behind our chatbot, you will need a Gemini API key. To get one, head over Google AI Studio. It is completely free for developers. Click on the blue Gemini API key button in the top left, select your project and click Create API key. Copy this key and make sure keep it secret. Do not paste it completely publicly or commit it in GitHub. Our Google security scanners will automatically revoke it. Once you have your key, you can paste it directly into your Databricks app setting under Gemini API key environment variable or enter it in setting cog of the dashboard portal. We have an agent chat engine. This is where the magic happens. When you ask a question, the agent doesn't just give you a flat answer. It shows you its full chain of thought. You can expand the agent step panel to watch the router, analyze your intent, class the database retrieval tool, execute the SQL query on Databricks, and write a structured timeline trajectory update. It bridges the gap between natural conversation and raw data lakes. We have the analytics dashboard. This page queries our Delta Lake table on the fly to aggregate metrics. It displays our total order volume, overall gross sales, and the exact count of active orders in processing. Below the metrics, we have dynamic visual charts, a status distribution donut chart, a product sale breakdown bar chart, and a daily sale volume line chart. This gives operations teams to an instant real-time overview of the business. We have the Database Explorer tab. This is paginated database that lets you browse the raw records from the Delta table. You can type any customer name, email address, city, or any order ID in the search bar or filter the list by status. This makes searching through thousands of records incredibly fast, querying our cloud storage directly.